Hello everyone. In previous class we discussed about what is oscillator, the classification of oscillators, RC phase shift oscillator and LC oscillator. So in this lecture we will study about what is Hartley oscillators, मतलब ये oscillators क्या होता है, what is the circuit diagram of Hartley oscillators, working as well as the application of Hartley oscillators. After this we will move on the Colpitts oscillators. इसमें भी हम देखेंगे कि Colpitts oscillators क्या है, circuit diagram इसका कैसा रहेगा और working as well as the application of Colpitts oscillator. And finally the reference of this presentation. So in this lecture we cover these two oscillators in detail form. So let's start with topic 1, oscillator introduction. ये ऑलरेडी हमने पहले वाली स्लाइड में देखा था, बट फिर भी मैं आपको केवल उसमें ऑसिलेटर का डेफिनेशन बस बताऊंगा. उसके बाद हम मूव करेंगे हार्टले और कोलपिट्स ऑसिलेटर की तरफ. सो व्हाट इज ऑसिलेटर? एन ऑसिलेटर जनरेट्स आउटपुट विदाउट एनी इनपुट सिग्नल. जो हमारा एम्पलीफायर सर्किट होता है उसमें हम इनपुट देते हैं, इनपुट सिग्नल, जिसको एम्पलीफायर उसके पावर लेवल को बूस्ट अप करके हमें आउटपुट में सिग्नल प्रोवाइड करता है. बट ऑसिलेटर की केस में हमें इनपुट सिग्नल नहीं देना होता है, केवल हमारा डीसी सप्लाई के थ्रू ही हम आउटपुट को जनरेट कर सकते हैं. ऑसिलेटर एन इलेक्ट्रॉनिक सर्किट which convert DC energy into AC at a very high frequency. तो मेन फंक्शन जो ऑसिलेटर का है वो क्या है? पहले तो ये इट इज अ इलेक्ट्रॉनिक डिवाइस, एक इलेक्ट्रॉनिक डिवाइस सर्किटरी है जो कि कन्वर्ट करता है डीसी एनर्जी को एसी एनर्जी में एट वेरी हाई फ्रीक्वेंसी. ये बहुत ही इंपॉर्टेंट है कि बहुत हाई फ्रीक्वेंसी में एसी में कन्वर्ट करता है. फ्रीक्वेंसी क्या होता है? नंबर ऑफ साइकिल पासिंग थ्रू 1 सेकेंड इज कॉल्ड द फ्रीक्वेंसी. एन एम्पलीफायर with a positive feedback can be understood as an oscillator. The next topic is Hartley oscillator. The Hartley oscillator design uses two inductive coils in series with a parallel capacitor to form its resonance tank circuit, reducing sinusoidal oscillation. एक्चुअली जो हमारे सारे के सारे ऑसिलेटर सर्किट हैं वो डिपेंड करते हैं रेजोनेंस कंडीशन पे. सो पहले हम समझ लेते हैं रेजोनेंस क्या होता है. रेजोनेंस का मतलब होता है जब हमारा इंडक्टिव रिएक्टेंस कैपेसिटिव रिएक्टेंस के बराबर हो जाता है, तो इस कंडीशन में रेजोनेंस होता है. मैथमेटिकली फॉर्म में अगर हम बोले तो XL इज इक्वल टू अगर XC हो गया, सो दिस इज कॉल्ड द रेजोनेंस कंडीशन. और रेजोनेंस जो होता है वो दो टाइप का होता है, एक सीरीज रेजोनेंस और एक पैरेलल रेजोनेंस. सीरीज रेजोनेंस क्या होगा? इफ द सर्किट एलिमेंट RLC are connected in series, so the known as series resonance circuit. And if the RLC elements are connected parallel to each other, so the circuit is known as parallel resonance circuit. रेजोनेंस सर्किट कब बनेंगे? ये जब XL इज इक्वल टू XC होगा. जब तक हमारा XL इज इक्वल टू XC नहीं है तब तक हम इनको रेजोनेंस सर्किट नहीं बोल सकते, इनको हम सिंपल सीरीज और पैरेलल सर्किट बोलेंगे. One of the main disadvantage of basic LC oscillator circuit we looked at in a previous tutorial or previous lecture is that they have no means of controlling the amplitude of oscillation, and also it's difficult to true the oscillation or oscillator to the required frequency. If the cumulative electromagnetic coupling between L1 and L2 L1 is called inductor 1 and L2 is called the inductor 2, is too small, there would be insufficient feedback and the oscillations would eventually die away to zero. Likewise, if the feedback was too strong, the oscillations would continue to increase in amplitude until they were limited by circuit condition, producing signal distortion. So it become very difficult to tune the oscillator. तो LC oscillator में हमें सबसे बड़ी प्रॉब्लम क्या आती है? ट्यूनिंग. However, it is possible to feedback exactly the right amount of the voltage for a constant amplitude oscillation. If we feedback more than it necessary, the amplitude of the oscillation can be controlled by biasing the amplifier in such a way that if the oscillation increase in amplitude, the bias is increased and the gain of the amplifier is reduced. If the amplitude of the oscillation decrease, the bias decrease and the gain of the amplifier increase, thus increasing the feedback. In this way, the amplitude of the oscillation are kept constant using a process known as automatic base bias. So this is the circuit diagram for Hartley Oscillator tank circuit. In diagram 1, one capacitor and inductor is connected. In second diagram, the inductor is splitted into two parts, L1 and L2. One big advantage of automatic base bias in a voltage controlled oscillator is that the oscillator can be made more efficient by providing a class B bias or even a class C bias condition of the transistor. This has the advantage that the collector current only flow during the part of the oscillation cycle, so the quiescent collector current is very small. Then the self-tuning base oscillator circuit forms one of the most common type of LC parallel resonant feedback oscillation circuit, configure called the Hartley Oscillator circuit. तो जो हमारे LC oscillator में प्रॉब्लम था ट्यूनिंग का, वो हम बाय यूजिंग हार्टले ऑसिलेटर उसको हम रिमूव कर सकते हैं और मिनिमाइज कर सकते हैं. In the Hartley oscillators, the tuned LC circuit is connected between the collector and the base of a transistor amplifier. As far as the oscillatory voltage is concerned, the emitter is connected to the tapping point on the tuned circuit coil. The feedback part of the tuned LC tank circuit is taken from the center tape of the inductor coil or even two separate coils in series which are in parallel with a variable capacitor C as shown in a figure. The Hartley circuit is often referred to as a split inductance oscillators because the coil L is center taped. Center taped का मतलब हमने L coil को two part में divide कर दिया. In effect, inductance L act like two separate coils and very close proximity with the current flowing through coil section XY induced a signal into coil section YZ below. A Hartley oscillator circuit can be made from any configurations that use either a single tipped coil or a pair of series connected coil in parallel with a single capacitor as shown in a figure. So this is the basic Hartley oscillator circuit diagram. In this diagram, the transistor is connected. This is the NPN transistor. 4 resistance R1, R2, R3 and R4 is used in the circuit. 3 capacitors C1, C2 and C3 are connected. And connect one LC tank circuit. जो अभी हमने देखा था LC tank circuit, इसमें इंडक्टर कॉइल को हमने दो पार्ट में डिवाइड किया है सेंटर टेप करके, and one capacitor is connected, and the arrow is indicate known as the variable capacitor. When the circuit is oscillating, the voltage at point X this is the point X related to the point Y. So X point is related to collector, Y point related to emitter and Z point related to base of the transistor circuit. So the point X related to point Y is 180 degree out of phase with the voltage at the point Z related to point Y. At the frequency of oscillation, the impedance of the collector load is resistive and an increase in base voltage cause a decrease in collector voltage. Thus, there is a 180 degree phase change in the voltage between the base and collector, and this along with the original 180 degree phase shift in the feedback loop provides the correct phase relationship of positive feedback for oscillations to be maintained. The amount of feedback depends upon the positive of the tapping point. Tapping से हम कुछ नहीं करते, बस tapping से हम क्या करते हैं, coil को 2 पार्ट में डिवाइड कर लेते हैं. So tapping point of the inductor, if this is moved nearer to the collector, the amount of feedback is increased, but the output taken between the collector and the earth is reduced and vice versa. Resistor R1 and R2 provide the usual stabilizing DC bias for the transistor in the normal manner, while the capacitor acts as DC blocking capacitor. In this Hartley oscillator circuit, the DC collector current flow through part of the coil, and for the reason the circuit is said to be series feed with the frequency of oscillation of the Hartley oscillators being given as f is equal to 1 upon 2 pi under root LC. This is called the resonance frequency. So L की जगह हमने LT लिया हुआ है. LT is called the tapped inductor. So LT is equal to L1 plus L2 plus 2M. Note, LT is the total cumulative coupled inductance if two separate coils are used, including their mutual inductance M. So this is the resonance frequency in a Hartley oscillator. The frequency of oscillation can be adjusted by varying the tuning capacitor C or by the varying the position of the iron dust core inside the coil, giving an output over the wide range of the frequency, making it very easy to tune. Also, the Hartley oscillator produces an output amplitude which is constant over the entire frequency range. Hartley oscillator की दो बहुत ही इंपॉर्टेंट जो एडवांटेजेस हैं, पहला एक तो सेल्फ ट्यूनिंग के लिए हम इसका यूज करते हैं, और दूसरा जो आउटपुट प्रोवाइड कराता है वो कांस्टेंट होता है एंटायर फ्रीक्वेंसी रेंज के लिए. As well as the series feed Hartley oscillators above, it is also possible to connect the tune tank circuit across the amplifier as a shunt feed oscillator as so below. So next is a shunt field Hartley oscillator circuit. पहले वाले सर्किट में हमने देखा था सीरीज में कनेक्टेड था, इसलिए हमने उसको सीरीज फीड बोला. एंड द सेकंड सर्किट इज shunt feed Hartley oscillator circuit. In a shunt fed Hartley oscillator circuit, both the AC and DC components of the collector current have separate path around the circuit. Since the DC component is blocked by the capacitor C2 on the DC flow through the inductor coil L, and less power is wasted in the tune circuit. The radio frequency coil RFC L2 is an RF tube which has a high reactance at a frequency of oscillation, so that the most of the RF current is applied to LC tuning tank circuit by capacitor C2 as the DC component passes through L2 to the power supply. A resistor could be used in place of the RFC coil L2, but the efficiency would be less. Next is a Hartley oscillator example number 1. A Hartley oscillator circuit having two individual inductors of 0.5 millihenry each are designed to resonate in parallel with a variable capacitor that can be adjusted between 100 picofarad and 500 picofarad. Determine the upper and lower frequencies of the oscillation and also the Hartley oscillator bandwidth. इस एग्जाम्पल से हम समझते हैं कि कैसे हम निकाल सकते हैं फ्रीक्वेंसी इन अ हार्टले ऑसिलेटर सर्किट. सो फॉर द above we calculate the frequency of oscillations for a Hartley oscillator as FR is equal to frequency को फार्मूला भी हमने पढ़ा 1/2 pi under root LT into C. The circuit consists of two inductive coil in series, so the total inductance is given as LT is equal to L1 plus L2. Put the value of L1 and L2, so 0.5 millihenry plus 0.5 millihenry is equal to 1 millihenry. Now calculate the Hartley oscillator upper frequency. So FH is equal to 1/2 pi under root of 1 millihenry into 100 picofarad. अपर फ्रीक्वेंसी की वैल्यू हमें दी हुई है, सी की वैल्यू भी हमें दी है. सो वी कैन कैलकुलेट 1/6.283 under root 1 into 10 raised to power minus 13. So we get 503.228 hertz. Now this is the upper frequency, or we can say that higher frequency FH is equal to 503 kilohertz. Now next we calculate the lower frequency by using Hartley oscillators. So FL is equal to 1/2 pi under root 1 millihenry into 500 picofarad. Put the value of L, LT and C. So calculate this is equal to 1/6.283 under root of 5 into 10 raised to power minus 13. So we get 225050 hertz. Or we can say that the lower frequency FL is equal to 225 kilohertz. Now next we calculate the Hartley oscillator bandwidth. तो bandwidth का जो फॉर्मूला होता है वो होता है हायर फ्रीक्वेंसी माइनस ऑफ लोअर फ्रीक्वेंसी. हायर फ्रीक्वेंसी की वैल्यू अभी हमने कैलकुलेट की है 503, lower frequency 225, so we get 278 kilohertz. This is the bandwidth. Next topic is Hartley oscillator using an op amps, means operational amplifier circuit. So this is the diagram for Hartley oscillator using an operational amplifier. As well as using a bipolar junction transistor BJT as the amplifier active stage of the Hartley oscillators. We can also use either a field effect transistor FET or a operational amplifier op-amps. The operation of op-amps Hartley oscillator is exactly same as for the transistorized version, with the frequency of operation calculated in the same manner. Consider the circuit shown in a figure. The advantages of constructing a Hartley oscillator using an operational amplifier as its active stage is that the gain of the operational amplifier can be very easily adjusted using a feedback resistor R1 and R2. As with the transistorized oscillator above, the gain of the circuit must be equal to or slightly greater than the ratio of L1 by L2. If the two inductive coils are wound onto a common core, the mutual inductance M exists, then the ratio becomes L1 plus M divided by L2 plus M. Next is the summary of the Hartley oscillator. Then to summarize, the Hartley oscillator consists of a parallel LC resonant tank circuit whose feedback is achieved by way of an inductive divider. Like most oscillator circuits, the Hartley oscillator exists in several forms, with the most common form being the transistor circuit above. The Hartley oscillator configuration has a tuned tank circuit with its resonance coil tapped to feed a fraction of the output signal back to the emitter of the transistor. Since the output of the transistor emitter is always in phase with the output of the collector, this feedback signal is positive. The oscillator or oscillating frequency, which is sine wave voltage, is determined by the resonance frequency of the tank circuit. In the next lecture about oscillator, we will look at the another type of LC oscillator circuit that is opposite to the Hartley oscillator, called the Colpitts oscillator. The Colpitts oscillators uses two capacitors in series to form a center-taped capacitor in parallel with a single inductance within its resonance tank circuit. So this is all about the Hartley oscillator. The next topic is Colpitts oscillator. The Colpitts oscillator design using two center-taped capacitors in series with a parallel inductor to form its resonance tank circuit, producing sinusoidal oscillation. In many ways, the Colpitts oscillator is the exact opposite of Hartley oscillator we looked at in the previous slides. Just like the Hartley oscillators, the tuned tank circuit consists of an LC resonance sub-circuit connected between the collector and the base of the single stage transistor amplifier, producing a sinusoidal output waveform. So this is the circuit diagram for Colpitts oscillator tank circuit. इसमें हमने इंडक्टर की जगह कैपेसिटर को सेंटर टेप्ड किया हुआ है। हार्टले ऑसिलेटर पे हमने क्या किया था, इंडक्टर को सेंटर टेप्ड किया था। The basic configuration of Colpitts oscillators resembles that of the Hartley oscillator, but the difference this time is that The center taping of the tank sub-circuit is now made at the junction of a capacitive voltage divider network instead of the taped autotransformer type inductor as in the Hartley oscillator. The Colpitts oscillators uses a capacitive voltage divider network as its feedback source. The two capacitors C1 and C2 are placed across a single common inductor L as shown in a figure. Then C1 and C2 and L from the tuned tank circuit with the condition of oscillation being Xc1 plus Xc2 is equal to XL. The same as for the Hartley oscillator circuit. The advantage of this type of capacitive circuit configuration is that with less self and mutual inductance within the tank circuit, frequency stability of the oscillator is improved along with the more simple design. इंडक्टर की जगह कैपेसिटर को सेंटर टेप करने से हमारा सेल्फ इंडक्टेंस और म्यूचुअल इंडक्टेंस जो है वो कम हो जाता है. As with the Hartley oscillator, the Colpitts oscillator uses a single stage bipolar transistor amplifier as the gain element which produce a sinusoidal output. Consider the circuit below. Next is a Colpitts oscillator circuit. So this is the circuit diagram for Colpitts oscillator. इसमें टैंक सर्किट में हमने कैपेसिटर वाला टैंक सर्किट यूज किया हुआ है और ट्रांजिस्टर एम्पलीफायर यूज किया है जिसमें हमने एनपीएन ट्रांजिस्टर का यूज किया हुआ है. The emitter terminal of the transistor is effectively connected to the junction of the two capacitors C1 and C2 which are connected in series and act as a simple voltage divider. When the power supply is firstly applied, the capacitors C1 and C2 charge up and then discharge through the coil L. The oscillation across the capacitors are applied to the base emitter junction and appear in the amplified at the collector output. Resistor R1 and R2 provide the usual stabilizing DC bias for the transistor in the normal manner while the additional capacitor act as the DC blocking bypass capacitor. A radio frequency choke RFC is used in the collector circuit to provide a high reactance, ideally open circuit, at the frequency of oscillation FR and a low resistance at DC to help start the oscillation. The required external phase shift is obtained in a similar manner to that in the Hartley oscillator circuit, with the required positive feedback obtained for sustained undamped oscillation. The amount of feedback is determined by the ratio of C1 and C2. These two capacitors are generally get together to provide a constant amount of feedback so that as one is adjusted and the other automatic follows. अगर हम एक को एडजस्ट करते हैं तो दूसरा ऑटोमेटिक उसको फॉलो करेगा. इस तरीके से कैपेसिटर दोनों कनेक्टेड होते हैं. The frequency of oscillation for a Colpitts oscillators is determined by the resonance frequency of the LC tank circuit and is given as the frequency FR is equal to 1 upon 2 pi under root of LCT, where CT is the capacitance of C1 and C2 connected in series and is given as 1 upon CT is equal to 1 upon C1 plus 1 upon C2, or CT is equal to C1 into C2 divided by C1 plus C2. This configurations of the transistor amplifier is a common emitter amplifier with the output signal 180 out of phase with regards to the input signal. The additional 180 phase shift required for oscillations is achieved by the fact that the two capacitors are connected together in series but in parallel with the inductive coil, resulting in overall phase shift of the circuit being 0 or 360 . The amount of feedback depends on the value of C1 and C2. We can see that the voltage across C1 is the same as the oscillator's output voltage, V out, and that of the voltage across C2 is the oscillator feedback voltage. Then the voltage across C1 will be much greater than that of across C2. Therefore, by changing the value of the capacitor C1 and C2, we can adjust the amount of the feedback voltage returned to the tank circuit. However, large amounts of the feedback may cause the output sine wave to become distorted, while a small amount of feedback may not allow the circuit to be oscillated. Then the amount of feedbacks developed by the Colpitts oscillator is based on the capacitor ratio of C1 and C2 and is what governs the excitation of the oscillator. The ratio is called feedback fraction and is given as simple as feedback fraction is equal to C1 by C2 in percentage form. Now next is a Colpitts oscillator example 1. A Colpitts circuit having two capacitors of 24 nanofarad and 240 nanofarad respectively are connected in parallel with an inductor of 10 millihenry. Determine the frequency of oscillation of the circuit, the feedback friction, and draw the circuit. हमारे पास कैपेसिटर C1 C2 दोनों की वैल्यू गिवन है और इंडक्टर की वैल्यू भी गिवन है. So the oscillation frequency for Colpitts oscillator is given as, we know that Fr is equal to 1 upon 2 pi under root of L into Ct in case of Colpitts oscillator. As the Colpitts circuit consists of two capacitors in series, so the total capacitance is therefore Ct is equal to 24 into 240 divided by 24 plus 240. So we get 21.82 nanofarad. Ct is equal to 21.82 nanofarad. Next is Colpitts Oscillator circuit. So this is the circuit diagram for Colpitts Oscillator with LC tank circuit. Next, Colpitts oscillators using an op-amps or operational amplifier. Just like the previous Hartley oscillators, as well as using a bipolar junction transistor BJT as the oscillator active stage, we can also an operational amplifier. The operation of operational amplifier Colpitts oscillator is exactly the same as the transistorized version with the frequency of operation calculated in the same manner. Consider the circuit below. So this is the circuit diagram for Colpitts oscillator with operational amplifier. Note that being an inverting amplifier configuration, the ratio of R2 by I1 set the amplifier gain. A minimum gain of 2.9 is required to start oscillation. Resistor R3 provide the required feedback to the LC tank circuit. The advantages of the Colpitts oscillator over the Hartley oscillators are that the Colpitts oscillator provide a more purer sinusoidal waveform due to the low impedance path of the capacitor at the high frequencies. Also, due to these capacitor reactance properties, the FET based Colpitts oscillators can operate at very high frequencies. Of course, any operational amplifier or FET used as the amplifying device must be able to operate at the required high frequencies. So, last is a summary of Colpitts oscillators. The Colpitts oscillator consists of a parallel LC resonant tank circuit whose feedback is achieved by way of capacitive divider. Like most oscillator circuits, the Colpitts oscillators exist in several forms, with the most common form being similar to the transistor circuit above. The central taping of the tank sub-circuit is made at the junction of a capacitive voltage divider network to feed a fraction of the output signal back to the emitter of the transistor. The two capacitors in series provide a 180-degree phase shift, which is inverted by another 180-degree to provide the required positive feedback. The oscillator frequency, which is a purer sine wave voltage, is determined by the resonance frequency of the tank circuit. All about the Colpitts oscillators. The next is the references. So these are the references of this presentation. And thank you for watching this video.